Hello students, I am Professor Awais Ahmed Hussaini, Assistant Professor in Mechanical Engineering Department at Sharad Institute of Technology, College of Engineering, Vietnam. Students, in this video we will discuss the numericals on vapor power cycle. In that we are going to study the problems on Rankine cycle as well as Carnot cycle. So let us start with the brief introduction of Carnot cycle. In previous videos related with that vapor power cycle, we already discussed how that Carnot cycle works. But here again I will give the brief introduction of Carnot cycle. So basically this is a theoretical cycle. This particular cycle is not implemented in actual practice because of some limitations. So it consists of total 4 processes. The process 1-2 indicates constant temperature heat addition process. Now second process, that is process 2-3, this is isentropic expansion process. Process 3-4 is isothermal compression process where heat is rejected. Now the fourth process is process 4-1. The name of this particular process is isentropic compression. Now this is PV and TS plot of Carnot cycle. So here you students keep in mind that the heat addition and heat rejection only takes place in heat addition process at constant temperature and heat rejection at constant temperature only. So here heat is added at process 1-2 and heat is rejected at process 3-4. Heat addition and heat rejection never takes place in case of the isentropic process. It may be isentropic expansion or it may be isentropic compression. So in both process 2-3 and process 4-1 there is no any kind of heat addition and there is no any kind of heat rejection takes place. So here in that TS diagram, here you will get idea about the process. Again the process 1-2 is nothing but heat addition process at constant temperature. Process 2-3 is related with that isentropic expansion process. And here in case of the isentropic process, here you will get idea that entropy, that is S, remains constant. So you can write S2 is equal to S3 in this particular case. Similar way 3-4 is related with the isothermal heat rejection process. Process 4-1 is related with isentropic compression process where entropy remains constant. You can write S1 is equal to S4. So that vertical lines indicates that entropy remains constant in case of the isentropic process. So now this is a formula of the heat addition. Heat addition is nothing but the change in entropy into absolute temperature. So that change in entropy is nothing but S2 minus S1. So here you will get idea when we talk about the process 1-2, the parameters are related with point 1 and 2 only. So S2 minus S1 is nothing but change in entropy, and that absolute temperature, here we consider that T1 as the absolute temperature. So this is a formula of the heat supplied in this particular case. Similar way you can write S2 minus S1 into T2 because the T1 and T2 both are same here because this particular process happen in case of the constant temperature process. So you can write T1 is equal to T2. So I just replace that T1 by T2 here. Similar way in case of the heat rejection process, that is HR, it happens in case of the process 3-4. So here the formula of the heat rejection again same as that of the heat supplied. The formula is change in entropy into absolute temperature, but this particular process is deal with point 3 and 4. But as we know that in case of the isentropic process, the entropy remains constant. So that S2 is nothing but S3 and S1 is nothing but S4. So that S3 minus S4 is replaced by S2 minus S1 because the entropy is constant. Means S2 is equal to S3 here and S1 is equal to S4 in this case. So I just replace that S3 minus S4 by S2 minus S1. and change in entropy. So that particular formula of the heat rejection is nothing but change in entropy into absolute temperature. So here I consider the absolute temperature means from where the process starts. In first case, that absolute temperature is T1. Now in second case, in case of the heat rejection, the absolute temperature is T3. So here I just write T3. But in case of the process 3-4, the temperature remains constant, means T3 is equal to T4. So here I just replace the value of T3 by T4. Here we will get the values of the heat supplied and heat rejection. Now, performance of any engine is calculated by efficiency. So, what is exactly that efficiency? That efficiency is nothing but work done upon heat absorbed or heat supplied. So, the formula of the efficiency is nothing but work done upon heat supplied. So, here I just put the values of the work done here. And what is exactly that work done is? Work done is nothing but HS minus HR. So I just put those terms here and I get these particular values. So work done is nothing but that S2 minus S1 and T1 minus T3 here. And in denominator heat absorbed, the meaning of that heat absorbed is nothing but S2 minus S1 into that T1. T1 and T2 both are same, no doubt. Here I take that T1. Okay. Now at the end we will get efficiency T1 minus T3 upon T1. The meaning is 1 minus T3 upon T1. So this is the main efficiency of the Carnot cycle. Similar way, students, in case of the Rankine cycle, the components are the same as that of the Carnot cycle, but the only difference is in replacement of the compressor by the pump. But this particular Rankine cycle is practical one and it is implemented in actual practice in case of the steam power plant. So this is the boiler where we create the steam. Further that steam is expanded in the steam turbine. So generator is placed here in order to produce an electricity. Now whatever the steam is remaining, it enters in the condenser where it gets condensed, means the steam get converted into liquid. Further that liquid, that is water, enters in the boiler through the feed pump. So this is the main construction of the Rankine cycle. We already discussed theoretical part of the Rankine cycle in previous videos. This is the PV and TS diagram of the Rankine cycle. The process 1-2 is nothing but isothermal expansion. Process 2-3 is nothing but isentropic expansion. Process 3-4 is nothing but isothermal compression. And the process 4-1 is nothing but that warming operation where water gets little bit heated and further it enters in that particular boiler. So here also the heat addition and heat rejection takes place only in case of the process 1-2 and process 3-4. Similar way, heat addition is also possible in case of the Rankine cycle in the process 4-1. Okay, but in case of the isentropic process, there is no any kind of the heat is added and there is no any kind of the heat rejection takes place. Now students, these are some important terms it is required while solving the numericals, and in this way we can calculate the performance of the Rankine cycles. So while in order to solve the numericals on the Carnot cycle, we must have to know what is heat supplied, what is heat rejection, and on the basis of that we will get the value of the work done. Work done is equal to supplied minus heat rejection, and after that we will get that particular formula of the efficiency. That efficiency is nothing but that work done upon heat supplied. By putting all values we will get the formula of that Carnot cycle. But here these are some important terms are required while solving the numericals related with the Rankine cycle. So the first important term is efficiency ratio. So here the efficiency ratio is defined as the ratio of the thermal efficiency to Rankine efficiency. So it is defined as the ratio of thermal efficiency, that is actual cycle efficiency, to Rankine efficiency. Okay, so efficiency ratio is equal to thermal efficiency upon Rankine efficiency. And students, the formula of the Rankine cycle or that particular Rankine efficiency is that H2 minus H3 upon H2 minus HF3. I repeat once again, the formula of the Rankine cycle or that Rankine efficiency is H2 minus H3 upon H2 minus HF3. So, but here that thermal efficiency is calculated by the formula. Thermal efficiency is equal to heat equivalent to 1 kilowatt hour upon total heat supplied to the steam per kilowatt hour. So the formula is 3600 into P, that P stands for that power, upon M into H2 minus HF3. The value of H2 and HF3 we will get from the steam table. So don't worry about that particular term. So here that MS is nothing but the mass, that P is nothing but power in kilowatt. The second important term is work ratio. So the work ratio is defined as the ratio of net work output to the gross output, and that net work output is nothing but the turbine work minus compressor work, and that gross output is calculated by that turbine work. So here that work ratio is nothing but the ratio of net work output upon gross output, and that net work output is equal to turbine work minus compressor work upon turbine work. We will get every parameter from the steam table while calculating this turbine work and that particular gross output. Now the third important and most important point is related with the Rankine cycle is specific steam consumption, that is SSC. So it is known as the steam rate of the specific rate of the flow of the steam, and it is defined as the mass of the steam that must be supplied to steam engine or turbine in order to develop a unit amount of work or power output. I repeat once again, that specific steam consumption is nothing but, or it is defined as the mass of the steam that must be supplied to a steam engine or turbine in order to develop a unit amount of work or power. So the formula of the specific steam consumption is 3600 upon H2 minus H3, and the unit of that particular SSC is kg per kilowatt hour. So here 1 kilowatt hour is equal to 3600 kilojoule. Here you will get idea about how that specific steam consumption is to be calculated. Now students, we will discuss the first problem or Carnot cycle. So here the problem is a power plant is supplied with dry saturated steam at a pressure of 16 bar and exhaust at 0.2 bar. Using steam table, find efficiency of the Carnot cycle. I repeat once again. A power plant is supplied with dry saturated steam at a pressure of 16 bar and exhaust at 0.2 bar. The meaning is, so whatever boiler is used in that particular power plant which generate the pressure around 16 bar, and when after expansion process in the turbine, when it exhausted, the pressure is around 0.2 bar. So we have to calculate the Carnot efficiency with the help of steam table. So here they mention we have to prefer that steam table. There are two methods to calculate the efficiency or parameters. One is steam table and second one and most important one is molar chart. So here we calculate the performance by using steam table only. So here I just write the value of the P1, that is 16 bar, and the value of the P2 is 0.2 bar. There is no need of the conversion of the unit. So, but we must have to calculate the efficiency. So while calculating the efficiency, we must have to know the formula of the Carnot cycle. The formula of Carnot cycle efficiency is T1 minus T3 upon T1. I repeat once again, efficiency is equal to T1 minus T3 upon T1. So we must have to know these two temperatures. One is T1 and another one is T3. So students, we must have to calculate that T1 with the help of steam table. So while calculating the value of the T1, we have to refer the pressure P1. So pressure P1 is equal to 16 bar. So from the saturated steam table, and one more important thing is, here the condition of the steam is mentioned. The steam which is removing from the boiler is dry saturated, means the condition is given. So we must have to refer the steam table of that dry saturated steam. So now corresponding to 16 bar pressure, the temperature is around 201.4 degree centigrade. So T1 is equal to 201.4 degree centigrade, and at the end we have to convert it into Kelvin by adding 273. So the value of the T1 is 474.4 Kelvin. Now the second one is, second pressure is given, that is P2 around 0.2 bar. Now corresponding to that 0.2 bar, we have to calculate the value of the T3. So corresponding to that 0.2 bar pressure, the temperature is around 60.1 degree centigrade. So again we will convert it into Kelvin by adding 273. So here I show you how those values is calculated with the help of steam table. So students, here you will get the idea about the saturated steam table and how the temperature is calculated. So here the first column is related with the pressure. In that, here we consider the 16 bar because it is mentioned in the problem. So the next column is related with the temperature. So the adjacent value of that pressure is temperature. So for 16 bar, temperature is around 201.4. So here this particular value comes, right? Now similar way, corresponding to pressure P2, we are calculating that T3 with the help of steam table. Similar way, here the pressure is around 0.2. Now its adjacent value is temperature, and for that 0.2 bar pressure, the value of the temperature is 60.09. So I just 60.09, it's around 1. So 60.1 is the temperature. After that, we just put those values in that main standard formula, you will get answer. After that, you just multiply it by 100, you will get answer in percentage. So the overall efficiency, that is Carnot efficiency, is 29.8%. Now students, we will take the second numerical based on Carnot cycle. So our main focus on the problems on Rankine cycle, because this is the most important numericals related to exam point of view. But you must have to know how that performance of the Rankine cycle, that Carnot cycle, is calculated. So here we will take another problem on Carnot cycle. In a Carnot cycle, the heat is supplied at 350 degree Celsius and is rejected at 25 degree Celsius. The working fluid is water, which while receiving heat evaporates from liquid at 350 degrees Celsius to steam at 350 degrees centigrade from the steam table. The entropy change for this process is 1.438 kilojoule per kg Kelvin. If the cycle operates on a stationary mass of 1 kg of water, find heat supplied, work done, heat rejection, and what is the pressure of the water during heat rejection. These all parameters we have to calculate. So the problem is very simple. In that they mention the heat is supplied at 350 degree centigrade. Means for that particular boiler pressure the temperature is around 350 degree centigrade. So I noted that T1 is equal to 350 degree centigrade. After that I just convert that temperature to Kelvin by adding 273. Now the second temperature is given, that is rejected, that particular heat is rejected at 25 degree centigrade. Means after expansion from the turbine the temperature is around 25 degree centigrade, and we just noted that T3 because T1 and T3 are the absolute temperature. In Carnot formula we use both T1 and T3 only. So here that T3 is equal to 25 degree centigrade, and I just convert that particular value to Kelvin by adding 273, and here the entropy change for this process is 1.438 kilojoule per kg Kelvin. So here change in entropy means S2 minus S1 is equal to 1.438 kilojoule per kg Kelvin. So these are the given parameters in the numerical, and we must have to calculate heat supplied, work done, and heat rejected. So we know all formulas. In previous slide here we discussed what is the formula of the heat supplied. That heat supplied is equal to S2 minus S1 into T1, that is S2 minus S1 into T2. Similar way, heat rejection is equal to S2 minus S1 into T3, that is S2 minus S1 into T4. Similar way, here you will get idea about the formula of the heat supplied. The formula of the heat supplied is change in entropy into absolute temperature. So here the change in entropy is that S2 minus S1 and absolute temperature is T1. So I just put the values. S2 minus S1 it is already mentioned here, that is 1.438. I just mentioned here, and that T1 is already given in Kelvin 623. So I just put the value here, and I get the answer of the heat supplied in kilojoule per kg. Similar way, the work done is calculated by the using formula heat supplied minus heat rejected. Heat supplied minus heat rejected is nothing but work done. So here by partial fraction method we get these values. Here also in previous slides the formula of the work done is S2 minus S1 into T1 minus T3. So here I just put the value of S2 minus S1 into T1 minus T3. The value of S2 minus S1, that is change in entropy, is already given in the numerical. So I just put that value here, and the values of T1 and T3 are already given in the problem. So T1 is that 350 degree centigrade, and I just converted it into Kelvin here. Similar way that T3 25 degree centigrade, and finally I converted it into Kelvin. So I put those values. So here I get the answer of the work done in terms of kilojoule per kg. So the work done is around 467.35 kilojoule per kg. Now the time has to come to calculate the heat rejected per cycle. The formula is S2 minus S1 into T3. In wording, the meaning of this formula is change in entropy into absolute temperature. So here absolute temperature is T3 in case of the heat rejection, and in case of the heat supplied the absolute temperature is T1. and in case of the heat rejection process, the absolute temperature is T3. So that change in entropy into absolute temperature is nothing but that heat rejection. The value of the change in entropy is already mentioned in the problem here. So, and T3 value is also given. After that we will get answer of 428.52 in kilojoule per kg. In this way we get all values of the heat supplied, work done and heat rejection by using simple formula of heat supplied, work done and heat rejection. Similar way, they want what is the pressure of the water during the heat reception. So here we must have to calculate pressures corresponding to that particular 350 degree centigrade and 25 degree centigrade. Okay, so in receptions means at entry point. So in steam table corresponding to that 350 degree centigrade, you just check the adjacent column and definitely it is a pressure, and you will get answer of that particular pressure with the help of the steam table. So in this way we solve the simple numericals on the Carnot cycle. So most important thing in case of the Carnot cycle is they have more focus on basic simple formula of the heat supplied, heat rejection, work done, efficiency. That's it. So this is all about numericals, simple numericals on vapor power cycle. In that we discussed the numerical on Carnot cycle. Our next video is most important. In that video we will discuss how to solve the numericals related with the Rankine cycle. Thank you.